Good morning. There's been a bit of confusion over my title. At times it's been Visual Analytics in the Wild, and initially it was something like Analysis of Social Media Data, and the second title is actually a more accurate reflection of what the talk is all about. But I thought Visual Analytics in the Wild was quite a nice title. I just wish I had a talk to go with it. I guess what's wild about this talk is that we are using some real data that I'll talk about later on. And before I really get into the presentation, I have to thank a bunch of postdocs who have helped develop the ideas that I'm going to talk about, particularly Erwin Martelo, who unfortunately was so successful at what he did that Google spotted some of his publications, and he now works in Mountain View. And then two current postdocs that I have, who are Maria Grazia Vigliotti and Donald Simi. So what I'm going to do is give some introductory material. I'm then going to spend most of my presentation talking about community detection, and then finally I want to talk about predicting influence. I realised on the way up from Hendon Central Station that normally when I give a lecture I reckon to get through about 12 slides during the hour, and I suddenly realised that I have 35 slides, although some of them are like this one here, so they won't take very long once I get into my stride. But there is quite a lot of material here. I think Nisha and Simon have copies of my slides, and hopefully those will be made available to you so that you can look at them at your leisure, because I guess we'll have to go through them fairly quickly. What we've been interested in my group are a variety of data analytics for social media data, or more generally, the kind of data that arises in the investigation of organised crime. So we've been very interested in spotting anomalous behaviour. We've done quite a bit of work on anomaly detection, which I'm not really going to talk about very much today. We've done a lot of work on detection of communities, particularly taking social media data and detecting sub-communities within a network, and also most particularly looking at how those sub-communities change over time. And then very recently we've been harvesting quite a lot of data from Twitter and looking at this problem of predicting influence. And right at the end, we'll certainly get to the end, but whether we get to my last slide, right at the end, if we do get to my last slide, I'll say a little bit about this final problem, which is a problem that's of interest to people, certainly who are investigating crime, which is that you may have a partial picture of a network and you're interested to spot where missing links might be. And the predicting influence work we've done has really been a precursor to identifying that missing information. So just a brief word about what I mean by community detection. So communities, very simply, are just groups of nodes within a network that are more densely connected between themselves than they are to the other nodes in the network. This is closely related to the notion of clustering, but unlike clusters, where you have an idea how you want to partition your set at the outset, with communities, you may not know how many communities there are in a network. So you have to grow them somewhat organically. And also, unlike clusters, communities can be very unequal in size, have very different density in the sense of the interconnections within a community, but most importantly can also be hierarchical. And the boundaries between communities may not be sharp. Clusters really are partitions of a set. Communities may actually have overlapping members. You may be a member of many communities at the same time. And depending on your scale, the granularity with which you look at a network, there will be different communities at those different scales. You may, for example, look at a country and see the country and see very little differentiation between the population of that country. But then if you look at a slightly finer level, you might see individual towns and cities and see the people who live there. And if you look at a still finer level, you'll see the members of Hendon Judo Club versus some other group within that region of a city. Finding communities is actually an NP hard problem, so we need to develop heuristics, and I'm not going to say a lot about the heuristics during this presentation because there isn't time to do everything, but I will give a couple of references during the presentation which have quite a lot of detail about that. And then to do the same thing about influence, what about influence? Well, I think the first bullet point there is just grabbing a definition from somewhere like Wikipedia, and I guess it's really a standard dictionary definition of what we mean by influence, which is the capacity of people to influence others, i.e. to produce effects or behaviour or actions of others by their own actions. And why we're interested in that is because it's relevant to crime analysis. For security, read crime here. It's going to be relevant to the work that I'll briefly touch on missing links. There are a number of different ways of measuring influence by observing the activity of individuals, seeing how their behaviour changes, and particularly we're going to be looking at influence in Twitter. So there, things like the follow accounts, the number of retweets, the number of mentions of individuals in other people's tweets are going to be important indicators of influence. I just thought I ought to have some visualizations, and this is an appalling visualization made even worse by the way I pasted it into this PDF file. But actually, this is a relevant community analysis. This isn't produced using our algorithms. It's actually produced using Gephi, in fact. This looks at a technical community of about 8,000 people, centered on, for those of you who are computer scientists, centered on this chap, Martin Odersky, who those of you who are computer scientists will know is the inventor of the Scala programming language. So we collected Twitter information about all the followers of Martin and did some analysis of it, which I'll tell you more about later on. But we also did some community detection on that population. And what you see just about, although the colour isn't very good, is that there's clearly a very large community down here, which is actually the community of people who work on Scala and follow Martin and talk about Scala on Twitter. Over here, there's actually, Martin started off his life as a functional programmer, and there's a kind of functional programming community over here. Up here, there's a community which is looking at typing issues in programs, and over here, I think it's probably a general sort of programming or Java community that also relate to Martin. So Gephi does produce quite a good visualization. I've just screwed it up in terms of incorporating it into this presentation. This one's a bit clearer. This is grabbed from a PowerPoint presentation that I've given in the past, which does use our community detection work. It looks at the 77 main characters that appear in the novel Les Miserables, and there are about 820 interactions between those characters, which correspond to co-appearance in parts of the plot of the novel. We run our algorithm, and basically there are various runs of it, but the plots coming down here are our algorithm trying to do a community detection on those networks. You see that both of them stabilize around about here, which is with 5 sub-communities within the 77 characters, and then after time they basically stabilize down here with about 3 sub-communities. And the gratifying thing about that is that this analysis was completely automatic, but basically the 5 communities you can actually associate with some of the major characters in the novel, and the switch to 3 communities corresponds to the point in time in the novel when Valjean actually comes out of jail, and then there's the merging of a number of communities. So it's not exactly a scientific validation, but it shows that the community detection work that I'm going to tell you about in a moment does a pretty good job in automatically inferring relationships between nodes in some kind of social network. So in thinking about how to construct these communities, one can take a sort of global approach where you actually look at the effect of adding a node to a community in terms of its relationship to the whole network, or there are local criteria which consider more changes just with respect to the immediate neighborhood of that node. And I'll talk about both approaches and do a little bit of comparison later on. So I'm now going to move on to the community detection part of the talk. And essentially, with community detection, I'll show you some algorithms, or at least some very abstract pseudocode for some algorithms in a short while. The approach of these is essentially that they construct the seed communities in some way, and then there's an iterative procedure of actually moving, first of all, nodes around into different communities, and secondly, then merging the communities that you've constructed by that, and then iterating all over again. And in order to understand when to stop iterating, and also to understand which nodes should be added to which communities, it's important to have some kind of optimization criteria. And the next few slides will look at some global optimization criteria, and then I've got a couple of slides on local optimization criteria before demonstrating the algorithms which you can use to find communities. So if we look at global criteria first, the classic approach is based on this notion called modularity, which is due to Newman and has been developed by Newman with a number of different co-authors. And basically, the essential optimization criteria is this quality measure, QM. The subscript M is indicating that we're talking about modularity, and Q is to remind us that we're talking about quality. So basically, you take a split of your network into a set of communities, and you can look at the quality of those communities using this measure. And this measure is constructed, although it may look daunting if you don't have a formal or mathematical background, it's actually doing something very simple. A is the adjacency matrix, so Aij tells you the number of links between node I and node J. This term here would be the number of links that you would expect between I and J if you had a completely random graph. So how is this computed? Well, basically, Di and Dj, as it says down here, are the degree or strength of the node I. Now, this is an undirected graph, so the strength is just the number of arcs which are incident upon that node. So Di is the number of arcs incident on I, and Dj is the number of arcs incident on J. We're assuming that there are a total of m edges in the graph, and in order to construct this random graph, we cut each edge in half, giving 2m. Okay? So the proportion of arcs which are incident on I is Di over 2m. The proportion of arcs that's incident on J is Dj over 2m. So actually, Di times Dj over 4m squared is the number of arcs you would get in a completely random graph if you were to generate such a thing. And Aij over 2m is the proportion of the total number of possible arcs that are actually incident on I and J in this particular network that we're looking at. That's what the adjacency matrix tells us. So what this negation is telling us is the difference between the number of arcs that there actually are between I and J versus the number of arcs that there would be if we took a completely random graph. Okay. The 2m is just factored out there, but it might have been clearer if this had been divided by 2m and this had been divided by 4m squared. And then there's this multiplication factor out here, which is basically 1 if I and J belong to the same community, and 0 if they don't. So this is about measuring the strength of the relative proportion of links that exists between I and j when I and j are in the same community versus what you would get if it was a completely random graph. So that's fine. That's the classic optimization criteria for building communities using. It's a global criteria. It looks at the whole graph. It has a few problems. They're listed at the bottom. Maybe the main problems are basically that it can have problems with resolution. It's difficult to. It actually, using this criteria, you tend to over-partition the graphs. And also, this is quite an important limitation, which is that many divisions of a graph into subcommunities would end up with the same QM measures. So there's no clear global optimum. There's no clear choice coming from this approach. So there are a number of newer, more recent approaches which try to address some of these issues. And many of them actually effectively introduce a parameter to deal with the resolution issue. So this is another measure which is based on modularity. Hopefully you recognize the measure here. It's very similar to the Newman measure, except there's a parameter gamma there. And this gamma effectively acts as a scale parameter, so you can tune it. And if you have a small value for gamma, then you're going to get larger communities. If you have a large value, you're going to get smaller communities. Okay, so I won't dwell on that because I hopefully have given you some idea of what's going on in the previous slide with the measure. So this is just a refinement which introduces some scaling measure. And then there's also another approach by Aranas and others, which actually effectively uses Newman's measure, but also has a scaling parameter, which is this R here. And R is there being multiplied by the identity matrix, which is a diagonal matrix which connects every node to itself. So you're adding self loops, which effectively increases the strength of each node in a community. Oh, sorry, each node in the graph. So again, with R, if you choose small values, which will be under sort of user control, so to speak, then you'll get larger communities. And if you choose larger values, you get smaller communities. Right. Then where we entered the story was, well, first of all, some other people entered the story, some biologists at Imperial, and came up with a different measure, which performs quite a lot better under some circumstances than either of the previous, or any of the previous approaches. And this is based on a notion called stability. So basically, it works out the quality of a community by looking at sorry, let me step back. It's based on the theory to a certain extent of Markov chains. The scale parameter is actually Markov time. So with a Markov chain, you can iterate the chain to actually get to, in the theory of Markov chains, to a stable point. Here, we're not going to go as far as that. We're just iterating it a few steps. How far you iterate effectively gives you your resolution parameter. The stability measure is really once you've assigned nodes to a particular community within a network, it's really measuring the chance that as you iterate over Markov time, it's measuring the chance that they actually stay within the community to which you've assigned them. So that's what stability is. It's stability effectively over Markov time. The construction is quite simple. The construction looks rather again like the Newman construction for measuring quality. The difference being that rather than taking the adjacency matrix, we're taking this matrix here, ATIJ. How is that computed? Well, the recipe for computing it is down here. It's relatively straightforward. Basically, D is a degree vector, so what that does is it assigns to every node the number of arcs which are incident upon it. And then big D is the diagonal matrix generated from that. So basically you spread that vector down the diagonal of a matrix and all the other elements are 0. And then you can construct a Markov chain, which is this M component here, by taking the adjacency matrix of the original network you start off with and pre-multiplying it by a matrix which is the reciprocal of this diagonal matrix. So in other words, all of the elements down the diagonal are no longer the degree, but 1 over the degree. Okay? Now, if you do that, then that multiplication actually produces a stochastic matrix, a Markov chain, effectively. And then you can iterate that Markov chain as many times as you like, which will correspond effectively to doing a random walk. And the elements within the matrix M give the probability of transitioning from one node to another. So n to the power t is the matrix that results from making a random walk of length t. And now we can construct this AT adjacency matrix, which is just the multiplication of D, the diagonal matrix from up here, with NT. And basically, if you want small communities, then you choose a small t. If you want large communities, you pick a larger t. The calculation of the quality then, once you've been through this process, is just the same as it was in the Newman case. But the t gives you the resolution parameter. And you will recall, you may recall, I hope you'll recall, the Les Miserables example I gave. There we saw that basically, well, we start off with very small communities because we actually put every node into a community by itself. So sorry, please don't get downhearted that I'm going backwards. I will eventually go forwards again. But these are the graphs for the evolution of communities using the stability optimization, a couple of variants of it. But basically, we start off with 77 communities because every node is in a single community. And then when we've been for a certain small t, we end up with 5 communities. So these are all these low values of t give quite small communities. And eventually, as t gets larger, we actually, in this case, stabilize on the 3 communities. So the longer t you go for, the larger communities you're going to end up with. Right, let's see if we can get back to where we were. Oh, sorry, we've gone too far. So that's the stability optimization, which is where we came into this, and we've done a lot of work on developing good algorithms and so on for working with that stability notion for identifying subcommunities in social networks. There's one other global criteria which is well studied in the literature, which is this one here, which isn't based on the Newman approach, so I thought I'd include it just to show you that modularity isn't at the heart of everything. There are other approaches. This is doing, in principle, the same kind of thing as Newman did, but not using random graphs. The J here is actually the complement of the adjacency matrix. So what this is kind of measuring is the difference between the connections you have in a community versus the connections you would have if the community were fully connected. Okay, so that's the kind of thing that it's trying to measure, and the gamma is the scaling parameter there, and it's essentially, if you like, giving you a way of tuning how important the missing connections are. And here, a small value of gamma would actually give you large communities, whilst a large value will give you denser communities. So those are all of the global criteria. So what about the local criteria? So these are criteria that look at a node and look at its immediate neighborhood and use some kind of measure of that local neighbourhood to decide whether or not the node should be shifted from one community to another. So there's just a couple that I wanted to show you, which is this work by Lancinetti. He's not in the audience, is he? So I can get away with the pronunciation there. This uses essentially a fitness measure for a community. The fitness measure is given here. Basically, it's looking at the number of internal links, which is K in C, and comparing that effectively with the number of seeing what proportion are internal versus the total number of links. So again, on the bottom here, we've got the number of internal links plus the number of links to external members, external nodes from the community. And again, there's a scaling parameter here, which is this alpha. So basically, that gives a fitness measure for each community. And then if we look at the process of adding a node to a community, we want to know what impact that will have on the fitness of the community that we're intending to add the node to. And we can compute that very simply like this. So this is the fitness of adding I to community C is the fitness of C where I has been added. So adding I will add a certain number of links to the internal links within the community. So this is where I has been added into the community, and this is where I has been taken away from the community, or isn't in the community. Certainly isn't in the community. So, and again, alpha is the tuning parameter. So if you take a large alpha, you get small communities, and if you take a small one, you get large communities. And then Huang and others have come up with a different local measure, which is based on this measure called structural similarity. And basically, I've been through enough of these in detail. That's horribly complicated. I'm not going to try and justify it. But basically, the gamma is the neighborhood of a node. There's a certain measure here, which is the weight, which is really what we've been calling D previously. And once you've got this notion of structural similarity, you can measure the tightness of a community and then use this measure to see whether it's actually worth adding a node into a community or not. So so basically, where we've got to is we've seen that there are a number of potential applications of community detection very briefly. We've then talked about optimization criteria for deciding when you've got a good partition of a network into a community. So the next thing I wanted to do is just briefly talk about the methods for using those optimization criteria to actually generate communities, as with, for example, Les Miserables example, or the way Gephi might approach things. And basically, there are just two algorithms, and really, for this, you may have to go back to look at the source papers, at least one of which has most of this material in much more detail, is available online. So you may have an opportunity to look at it during the course of this week. But in order to fit it onto a slide, I've abstracted it in a rather gross way. Both of these algorithms in a rather gross way, but you can see the general sort of structure from this, hopefully. So with the global criteria, we always start off assuming that every node is in an individual community. And then we've got these scale parameters, which were either called alpha, gamma, or R. But in this generic algorithm, I've called them P, just to keep you guessing. Basically, once you've got that initial assignment of nodes to communities, you can look at the network and apply the global criteria to the network and get a Q value. And then basically the core of the work here is in this loop, which has two internal loops. And basically this is, as long as you want to keep going, basically first of all you look at individual nodes and see whether nodes would be better moved from one community to another. Basically there's obviously a lot of computation behind this, because whether a node should be moved or not will depend on the difference it's going to make to the overall quality measure. So actually you work out the difference in the Q values depending on which optimization criteria you're working on. And if that's above a certain threshold, then that node would be a candidate for moving from one community to another. So if you unpack that, there's computation of changes in Q and deciding whether those changes are above a certain threshold so that it's worth moving the node. If it is worth moving the node, you still can't move the node if by moving the node from one community to another, its source community becomes disconnected. So you want to maintain that every community remains a community even when you take nodes out of it. So if there's a single interface between two sub-communities within a larger community, by removing that node, you'd suddenly get two communities, and you shouldn't do that. So that's what this breaking business is all about. You only move nodes if the connectivity of the community remains intact by moving those nodes. And then there's a second iteration, which now looks at the communities that you've got and sees whether there are any of those which are candidates for actually merging. So the first iteration was at the node level. The second iteration is actually looking at whole communities and seeing whether you get a better Q measure if you actually merge those communities. And if you do, then you update by merging the communities, and then you iterate around again. So this is an iterative process, basically at the end you've got a set of communities, and you've got a Q value for those for that particular scale, and then you can go around and iterate and look at different scales.
Can you just repeat 1 second why we can't break communities in the update step? You just mentioned it, and I wasn't able to update comp without breaking communities and update Q. You were saying don't break communities because.
Well, basically, I suppose really it's to do with this scale parameter. What we're trying to do is build the largest communities for that scale. So you don't actually want to take a community and split it up into a number of sub-communities. This is a building process where you're starting off with very small communities and moving to build as larger communities as you can for this scale. So breaking communities, I mean, given that you've got them, I mean, that's not a very good answer, because the next step is that you're going to start merging things again. So it could be that by breaking communities, you get other candidates for merging. But in the logic of the algorithm that we've actually tested and done, we decided we didn't ever want to take, unlike me flashing back to Les Miserables slide at every opportunity, we don't want to go backwards in terms of our construction of communities. So, yeah. That's it. Now, obviously, it's more than that. There's a lot abstracted away from that description, but it gives you a kind of idea of the way that works. The local criteria algorithms work in a slightly different way. Basically, here we've got an outer loop again for all scale parameters. If this is the first time through this loop, then we initialize again with every node as a potential community by itself. And then basically what we're going to do then is grow communities from the seeds tuned by P. So that's using the criteria for fitness and so on that I spoke about when I was looking at the local community slides, to decide whether nodes should be moved into other communities. If this isn't the first time through, then again use that criterion of fitness for the Lancachetti or the tightness computation for Huang. And basically, you do that for all of the communities that you currently have. So this effectively starts you off with a set of grown communities from the seeds, and this continues as you move up the scale. And then at the end, there's always the opportunity to actually look to see whether any of the communities you've got could be optimized further by merging. So those are, in very broad abstract outline, the global algorithm and the local algorithm. In fact, for each of the criteria, they're actually hard-coded with those criteria in our test suite. Because what we've done, again, if you have time during the summer school, you could go to this URL on the top and find that there are actually C++ procedures for both of those algorithms using the different criteria. This has been available for about a year now, and at least some of our project partners have managed to pick up these algorithms and incorporate them into some work that they've been doing on video clustering, and reported quite good experimental results. I've got some experiments, but again, the paper has many graphs from experiments, and I decided to concentrate on just a few. The scale parameters were sampled logarithmically over appropriate ranges for each of the algorithms. And in terms of looking at how the information is changing between successive iterations, we use this measure called normalized mutual information. So that's in some sense a way of measuring the progress of the refinement of communities that's resulting from the algorithms. This slide I'll probably skip over to a large extent. I'll just point out some highlights. This is this is describing normalized mutual information, which is this quality check between successive iterations. So it's an approach which comes from information theory. It uses notions of entropy and mutual information, which is this I measure. So these are completely standard information theoretic concepts. And then the normalized mutual information between two pairs of communities or two pairs of sets of communities is basically computed by taking 2 times the mutual information and dividing it by the individual entropies of the two communities. This ensures that NMI is actually a measure between 0 and 1. So essentially, it's like a probability of similarity between the two. I want to say partitions, the two divisions of the networks into sets of communities. This is just one example. This was using a very large, largest data set with about 10,000 nodes and 100,000 edges, with some, and these are the results for stability optimization. So for this particular run, there were just over 100 communities at small scale, and then eventually, so along the bottom here is mark-off time, and basically eventually we stabilize on a set of communities which is around about 50. So this is the normalized mutual information between a couple of iterations, and you can see that basically there's a switch here as the algorithm switches around about mark-off time of 4 or 5 to go from one set of communities to another. And the other charts here show the Q value changing over time, and another normalized mutual information measure. So basically what we've done, and this you can find in the paper, is look at an experiment with quite a large number of nodes, quite a large number of edges, using each of the global criteria and each of the local criteria, and plotted this kind of plot. And you can see all of those, as I say, in the paper that I'll refer to briefly. We looked at speed performance versus network size. So as the number of edges go up, these edges are times 1,000,000. Okay, so basically what we see is that for so the SO algorithms are the stability optimization algorithms. This is the non-modularity global check. These two are the modularity-based checks, and these two at the bottom are the local optimization criteria. And what we actually sort of see, you can't see the green very well, but it's actually here, and the purple is here. So the two local checks actually become exponential as the number of edges go up, which is a bit disappointing. The others really basically increase linearly. The difference between the three stability optimizations are, this is looking at the period in Markov time that we actually look at. So if we look between 0 and 1, then it will be on this plot, which is going quite nicely linearly as the number of edges increase. If we go from 0 up to 2 or 0 up to 4, the performance is a little bit disappointing, but not as bad as the local checks there, although this one doesn't look very promising. Okay, so there's a number of other plots that I have here. Again, this is looking at memory usage, and again we see actually that the stability optimizations for bigger scaling parameters don't do very well in terms of memory utilization. So there's a bit of a space leak there. We've actually got a new paper that's in under submission at the moment that actually introduces some multi-threading into the algorithm, and actually also introduces some other heuristics to address this memory usage thing. So we're actually getting better results than these graphs actually show with our more recent work. And that's speed performance according to how many scale parameters you look at during the iteration. Okay, so those are the two papers. This is the key one, which is actually published in the Computer Journal, first appeared electronically in January, and most of what I've spoken to you about is actually in this paper. This is the paper which addresses those rather disappointing graphs for stability optimization by introducing multi-threading and a slightly more sophisticated use of memory. And that one is available on arXiv, but is actually also under consideration for publication in a journal at the moment. I'm told I've only got 5 minutes, in fact only 4 now, so the last part of the talk was just about predicting influence, and basically I can go through this very rapidly. There is a paper submitted to the ACM conference on online social networks, which we will hear about in about 3 weeks' time. If it doesn't get accepted, it will be on arXiv, so you'll be able to see it anyway. If it does get accepted, it will be in the proceedings, hopefully in the beginning of October. It's about an experiment we did with Twitter. It's based on this community around Martin Odersky, so it's a Scala community. We've developed some new measures for ranking influential users called reach and buzz. Reach is actually not that exciting. It's very similar to PageRank, essentially. And there are also some Twitter specific ranking measures that we could use instead of PageRank. Buzz is about observation of influence relevant variables using a hidden Markov model. And it's actually a combination of reach and buzz, which leads to our influence ranking. Having done the theoretical work on the HMM and so on, we then actually had an online survey which was advertised through Twitter to the people who follow Martin Odersky to actually try and get some validation of the results. And basically, buzz is a combination, so I won't dwell on this because there isn't time, but buzz is a combination of retweets and mentions of individuals within Twitter messages. And basically, we conducted this survey, as I say. The survey actually ended up ranking 10, well, actually it ended up ranking 20, but these are the top 10 Twitter names that got ranked highly as influential people within the Scala community. This middle list is actually the list that we came up with using our reach and buzz measures. And the bold names here are names which, of course, appear also in here. Basically, after number 2, our ranking isn't the same order, but actually, from the point of view of the real application area that we're interested in, the precise ranking probably doesn't matter. It's just the case that these people are quite influential and need to be watched in some senses. And then this is the page rank ranking. So without buzz, you only get 4, whereas with reach and buzz, we actually got 6. Okay, so you can make of that what you will. So this is my final slide. This might be a good place to stop because I haven't got any more slides, but also because Simon's getting a bit fidgety. So this is about influence. So we want to use this. Sorry, this is about missing links. So we want to use some static tests for where links might be missing if we've got people who seem to have common friends, for example, or followers and aren't linked. If there are influencers for those people who are in common, then why aren't those people linked? Maybe influencer and influencee relationships. But then there are also some temporal features that we want to pick up on in terms of spotting missing links, which is about these kinds of homophily type measures that appear at the bottom there. Okay, well, thank you for your patience and your attentive listening. I'm aware that there's a lot of information in those slides, and it's difficult to absorb it, particularly after a few hours in the pub the night before. So hopefully you'll take time to look at the notes and maybe read some of the papers. And then please cite them, because in the UK, as you may be aware, citations are actually quite important in terms of research evaluation frameworks and so on.
Which is happening imminently.
Which is happening imminently, yep.
Thank you.
Thank you,
Chris.
So,